Hello everyone. I hope that you are enjoying good health. Welcome to another session of Robotics Lab. In this lab we shall learn and try to implement RRT and RRT star algorithm. If you remember from the lecture of motion planning and path planning, we studied RRT, or rapidly exploring random trees, and we also studied two different variants of this algorithm. So basically what this algorithm does is it finds searches or finds a path from start node to a goal node. So just a quick overview of RRT algorithm. So RRT stands for rapidly exploring random trees. So how this algorithm works, let's say we have, this is our workspace or configuration space, and so this is x-axis, we have y-axis. So the first thing is, this algorithm, it samples a point anywhere, but before that we have to define our start and goal nodes. So let's say this is our start node, let's call it start node, and this here is the goal node or target node we have here. So here we have obstacle, let's say we call this obstacle. Okay, so how this algorithm start is that it first include this start node in the tree, and once your start node is included in a tree, so then it samples a random point in your environment or in your workspace or configuration space. So let's say this is our random point here, and this is, we call it P1, and now what it does, the algorithm checks whether this point is inside obstacle or not, and if this point is not in obstacle, and then what it try to do is it try to connect this point with the nearest point in the tree. Okay, and it makes a new point at a distance d from this your nearest point of the tree, and this new point we call it, okay, we call it n1, and this is at a distance d from your nearest point. And the algorithm checks at whether this point is also not collision with the obstacle. Okay, the point and also this line, so it means that there is no obstacle here. If this is true, then this point n1 will be included in the tree. Okay, so we have, so first in the tree only was the point s, and then now we have included in the tree we have another point, it's called n1. Okay, and after that it will sample let's say one more point, we call it P2, and it will again check in the tree which is the nearest point, and let's say S is the nearest point in this tree. S is nearest to P2. So what it does, the algorithm makes a point N2 at a distance D from the S, or the nearest point, okay? And this, if this point N2 and this line is not in collision with the obstacle, then this point N2 will be included in the tree. So let's include this also in the tree. So similarly, by repeating this process, there will be more samples. Let's say if any sample is let's say if any sample lies inside the obstacle P3, then this can be rejected, okay? And yeah, so in this way, this process will keep repeating, and the tree will become bigger and bigger. And this process will be repeated in certain number of steps which are predefined, and the algorithm will stop when there is a node, the goal node is found within a certain radius or the diameter of the goal point, or when the goal point exactly found, then the algorithm will stop. And from here, what we do, we start to look for the parents of the nodes, like we did in previously in Dijkstra's algorithm, breadth first search. By following the parents of every node in the tree, we shall reach the start point, and this will be the path from your start point to your goal point, okay? So this is a brief explanation, you can say. If you want further details, then you have to refer to the lecture. And now we shall try to implement this in the Matlab. Okay, so for this we have to visit this website. I shall include the link of this website where you can download this 2-dimensional and 3-dimensional RRT star algorithm. You can have to just press this download button, or maybe you have to log in into Matlab, then press just download, and it will download into your this Matlab environment. And then you just have to, I have already downloaded it, and here you can see here we have this. And so we there are two folders, 2D and 3D. We are only now focusing on 2D. 3D is a little bit more complex. You can see there are some functions, and also this is RRT star.m. This is the main algorithm. The others, they are functions to avoid, to check the collision, and to steer. So let's start with explaining this algorithm, how it works and how. So since this algorithm has been already developed by some person, so we shall not reinvent the wheel. We shall take the code and try to understand it, how it works. So the name of this algorithm, as it is written, it's RRT star, but we can also use it as RRT algorithm. and I will show you how. Okay, so the author of this algorithm is Sai Vemprala, and so this is a 2D version. So here we have brief description: pick a random node, Q random, and then find the closest node Q near, and then you have to steer from Q near towards your random node, and then update the cost of reaching the, okay, this is for RRT star, but first we only consider the area for RRT algorithm. Okay, so first of all, clear variables. We have to clear all variables and close all. They say that Matlab says that this command is efficient as compared to the clear all. Okay, so that's why they use it. And then we have the x max and y max. We have 1000 and 1000. So it means that you can say that the distance is along x-axis 1000, y-axis also 1000. And then we have an obstacle here, and this obstacle is placed at so these are the 4 corners of the obstacle we have. So let's try to put it in the range of 100 and 100, make it a little bit smaller. And let's say the obstacle is at 50 and 50 and 50, and along the okay, I think these are the x and y coordinates of the starting coordinate of the starting point of the obstacle, and then we have, this will be the size along x and y axis. So let's make it on the x-axis, let's make it 40 and 40 here also. So this EPS, this is a distance for how far your new point will be steered toward the random point. If you remember this here, this distance d, where we are making this new point at a distance d from your start point. So this d is, in the code it is written as EPS. So this is 20, and we make it as, let's say, 2. And then we have number of nodes. These are the total number of samples or random samples that were made, and they are 3000, and we shall make them, let's say, 1000. So after 1000 samples, the algorithm will automatically stop. The algorithm can also stop if it finds the goal maybe earlier also. And then we have these starting coordinates of your start point, and here you have to give the goal coordinates of your goal point. Okay, so let's give them, let's say we have total 100 by 100, we have our configuration space. So let's say our target is located at 90 and 90. I hope that this will be this obstacle will not collide with this goal point, because 50 plus 40 is 90. Yeah, so let's make it a little bit less. We make it 30. 30, 30. So 30 plus 40, 70. So the size of the obstacle will be 70 on x and y axis. Okay, so next, in the next step, you see that we have added this, our start node in the tree, and the tree we call it nodes. So this is a tree we are creating here, and then there is a figure, and in this figure we are just plotting so we have defined the maximum range of the axis, and we have also defined that we have plotted the obstacle. And here actually the RRT algorithm starts. So the RRT algorithm, you see that there is a for loop from 1 to number of nodes, which is 1000 in this case. And what it does, there is a command here, and this command, what it does, it makes a random point, okay, within this, the range of 0 to 100, okay. So this command actually makes a random point from 0 to I think 1. But let's say if I type it here, for example, rand 1, and press enter, so you see that there is 0.7. So the range of this random point is 0.8, 0.8, 0.5, 0.6. Yeah, so the range will be from 0 to 1, and to make it compatible with our range, which is 0 to 100, we have to multiply it with our x range and the y range, and then we have to use this command floor to drop the variable, the decimal point, okay. So this will be our random point, which will have an x coordinate and also a y coordinate. And then in the next command, they have plotted this random point, and in the next step they say that, okay, break if the goal node is already reached. So here we check that if the goal node is reached, the algorithm will stop, okay. And then, but if the goal node is not reached, so what it does, it tries to find the nearest node to the random node in the tree. So using this for loop, what it does, it tries to find the nearest node. So you can see that. So how it does that, it measures a distance between your random point and all the points in the tree. Let's see again here. So when we here, if you remember, when we plotted when we sample this point P1, okay, so P1 point has to be connected with the tree, okay, at a distance d. So what it does, the algorithm, if the tree has, let's say, 5 points already included, 5 nodes, then the algorithm will measure the distance from P1 to all the nodes in the tree, and it will check which has the shortest distance, which has a minimum distance, and then it will try to connect with this shortest distance node. So that's what we are doing here. And then, yeah, here you can see that it will now use command minimum to find which point has a minimum distance in this tree. And then once you found it, and you call it, okay, this is our nearest point. So for let's see the example again. This P1 was a random point, and here we saw that, okay, S was our nearest point, because there was only one point in your tree. So we say that, okay, this was a random point, this was the nearest point, and we made a new point n1 at a distance d. So till now we have found the nearest point, and now we will make a new point. For the new point we shall use a function called steer. So you see that the function is located here, and if we try to open it, you see that what's going on here is this function steer. It accepts some parameters or variables called qrandom and qnear, and then we have value and we have EPS. EPS, you remember the EPS is the distance from your nearest point to the new point. Okay, and this is you can yourself define that how long this distance should be. Okay, so we have here, okay, so we call this function steer, and what this function does is it actually makes a new point q new at a distance EPS from the nearest point, and this is how we do that. These are some commands here, and the output of this function a will be returned to our this q new coordinates. So we now have a new point. In the next step, the algorithm checks whether the random point or the nearest point, they are not collision with the obstacle, or there is no obstacle between these 2 points. So for this purpose we use this function called no collision. This is defined here, and this function takes input arguments as qrand and qnear and the coordinates of the obstacle. So the random point and the nearest point, and then the obstacle coordinates. So this is how it checks the collision. So I think it checks for each coordinates of the obstacle that either the random point or your nearest point or a line connecting these 2 points, it is not present inside the coordinates of the obstacle. So this is how it checks, and the output of this function is either 1 or 0. Okay, so if there is a collision, then it will return 1, and if there is no collision, then it will, if there is no collision, it will return 1. Okay, and then the other steps will continue. But if there is collision, the function returns 0, and then you have directly, you will go at line 118, which is here, and yeah. So actually you don't do anything, you just discard this new point, and yeah, so this is no collision. And if there is no collision, it means that the next segment of the code will be executed, and in this code we have we will plot a line, and the line will be plotted between the nearest point to the new point. Okay, and along the x and y coordinates, and this will be plot will be instantaneously. And then what we do, we calculate the distance between the new point and the nearest point, and we can also add a cost. Because we haven't defined any cost, so we let it like this. We don't do anything here. So this is to calculate the cost of the new point. Okay, till here we have RRT algorithm completed. Okay, we have done everything. After that, we only have from here the RRT star. From line number 74, we have this code for RRT star algorithm, which modifies or rewires your tree and try to find the shortest path. Okay, but for RRT algorithm till here, I think this is enough. And after that, we can go to directly at line number 102. Okay, so between line number 74 to line number 100, this code is to make an RRT algorithm as RRT star algorithm. So we are not considering it yet now. We are only considering the RRT algorithm. One way is to do that, either to delete this code, but the other way is to make this R is equal to 0. Okay, so later I will explain how RRT star works and why we had made this 0. And we have made it 0, and then in the next step, what we have here, update parent to least cost from node. So this is also for RRT star. Okay, so this process will keep repeating this, adding nodes to the tree, and this process will keep repeating till number of steps is equal to number of nodes. For example, this process will keep repeating for 1000 times because we have defined number of nodes is equal to 1000. And once the number of nodes is finished, this for loop will end, or we have found the goal, the for loop will end. And then we try to find the distance between the goal and the nodes of the tree. Okay, and we have stored this distance as an array, and then we try to find which one has a minimum distance, and we try to then connect this node to our goal node. And so here we have added the goal node, okay, to the tree, to the nearest node to the tree. And then after that, we search backwards from goal to the start node, and we look for the parent node till we reach the start node. Here we are doing that. We said, okay, we have defined a variable called start, and here we have added a node, our goal node and its parent. Okay, and here we have drawn a line, and this line is between your goal node and the nearest nodes in the tree. Okay, and then we press hold on, and then what we do, we make the q end equal to the nodes, the previous node. So what's happening here, actually, we we are searching the parent of each node from your goal to your start point. And in this tree, we look for the nodes that were the parent node to the goal node. If we started from here, we look, okay, which one is a parent of the goal node, and this one is here. And then we came here, we said, okay, which one is parent of this node, and we came here, and we keep repeating this process till we reach the start point. Okay, now let's try to run this algorithm and see how it works. As you see that the tree is building rapidly in all directions, and somewhere here we have 90 by 90. Here we have the goal location where the arrow is, and till now the algorithm haven't found any goal, and it keeps exploring, and finally it has found the goal, or either the number of nodes, number of steps in the for loop, they are finished 1,000 times. And then what the algorithm does, it started to look for nodes backward and try to find a path from your start goal to your target node. So here, this one is our obstacle, and these cross points, they are the sample points, randomly sample points. There are like 1,000 of them. And yeah, and the black lines, they represent your tree. Okay, as you have seen that, you have noticed that not all the sample points are included in the tree. Okay, because we travel a certain distance from the nearest point to the new point. We don't include actually the sample point always. And you have also noticed that the tree is not going inside the obstacle, because here we are using this function called no collision. We have detected the collision, and if there is collision, we don't make the tree in this direction. So that's how the tree will not go inside the obstacle. It will always avoid the obstacle, and it will try to reach all possible free spaces. So yeah, now let's try to change some parameters. Now the distance, it was 2 first. Now let's make it like 8 and see what's the difference now. You see that now the distance between the points of the tree, they are larger. It's not smaller, and now you have more free space being explored. The tree, it explored more free space, and now you see that the path it looks different. So because this is a random algorithm, and every time it will find a different path, and the path will also not the shortest path. It will always be some, like you can say, feasible path. It will avoid obstacles. It will find the goal, but it's not a shortest path, as it's clear that shortest path will be from here, like this straight line, and from here straight line. Like if you use here Dijkstra's algorithm, you will have, it will be a shortest path then, but for that you need to decompose your configuration space or your environment into a grid or a graph, and then you can implement Dijkstra's algorithm. But for RRT algorithm, you don't need a grid or a graph. It actually makes its own graph, which is a tree, and then it tries to find a path, which is a feasible path that avoids obstacles and searches a goal. So yes, so now let's try to further decrease the EPS value or the distance. We make it 1, and let's see how the algorithm looks like. So this time you see that the algorithm, it's not exploring much of the free space. It tries to explore limited because the distance is less. So every new point that is added from the tree, it is at a smaller distance. Yeah, but the path, it looks much more, I would say, feasible as compared to the previous value, which was 8. The path was much more zigzag, but this one is, I would say, it's better acceptable as compared to the previous one. So this is how we can change the EPS value, but still you see that this path is not shortest. There are a lot of curves, there are a lot of zigzags, and this is not the optimal path or the shortest path. And we shall see in after some minutes that how we can solve this problem using RRT star algorithm. But let's explore some more variables here. So this is how we make obstacle, start and target position we have here, and then number of nodes. Let's try to decrease number of nodes. And where are the number of nodes? Yes, we have 1000. Let's make them 100 and see that. You see that there were less number of samples, only few hundred. So the algorithm failed to reach find the goal or the target position, and the tree finished here only. So all these are the sample points, but the tree have grown till here only, and then till here the algorithm stopped because the number of nodes were finished. And then what it does, it just simply connected your goal node to the nearest node in your tree, which is a straight line, but it doesn't make sense. It's not feasible because it is in collision with the obstacle. So yeah, so we have to increase number of nodes to 1000 at least. Okay, what else we can learn here is that we have steer function, and then we have plotted a line, collision, and yeah, so I think we have till here. Our RRT algorithm is complete, and now we see that how we can further optimize this RRT algorithm using by making it RRT star algorithm. Okay, so for that, first we need to quickly see that how we can do that. For the details you have to go through the lecture, but here I will just go through quickly. I will just review it. So this was a path that was found during the RRT algorithm, and of course I think this is not the shortest path or the optimal path. So the RRT star algorithm, what it does, and that it rewires your tree. Okay, for example, if you have here if you found a better or the shortest point within the radius r, then you can rewire your graph actually. For example, let's take a node, this node here, and we see that we defined a radius or a diameter that is r, and we say that okay, within this distance, let me define this radius with yellow color. We say that okay, within this radius r, we shall check whether we can further optimize the path or we can find the shortest path. So from this point, what an RRT star algorithm does extra, that it has an additional step in which it checks further the shortest distance from a current node to other nodes. For example, it will check that okay, going from this node to this node, let's say this is a node, I call it small n, okay, this is n, let me change the color because I think it's not visible. Okay, call it, okay, this is node n1. So from n1, this is node n2, and this is node n3. So this, in RRT star algorithm, what we do, we use an extra step which is called rewiring the tree, and in this step we look for, from the current node, we look for a further shortest path to other nodes. For example, going from n1 to n3, what RRT does, it goes from n1, n2 and n3, which is not of course the shortest path, but what RRT star does, it says okay, that shortest path from n1 to n3 is actually, this is the directly going from n1 to n3, not through n2. Okay, so what it does, it breaks the connections or the edges from here, and it makes a new connection from which is directly going from n1 to n3, and this process is called rewiring the graph. And this is how the RRT algorithm tries to find shortest path, and it is better as compared to RRT algorithm. Yeah, so now let's see how we can implement this thing in the Matlab. Okay, so till here we have already covered where we have checked the collision. This was RRT algorithm. So here now what we do, we defined an empty array which is q nearest, and we defined a radius r, and let the value of this radius is, let's say 5 meters. And so it means that within the radius of 5 meters we shall check and rewire our graph to optimize and to find the shortest path. Yeah, for that purpose there is a for loop, and then we have if condition, and in this condition we check the collision, whether there's a collision between the new node and existing nodes in the tree. So if this is collision free, then this function will return 1, and if there is a collision, then this function will return 0. There is also AND statement here, and then this condition must be true also. And what this condition says, it says that the distance between the new new node and the existing node in the tree. Okay, it should be less than your the radius, defined radius. So this means that you within a specific radius within a specific radius r, you are checking the nodes. Okay, you take this node as your current node or your new node, and then within this radius r, within this area, you check the you check simply which nodes are within this area. For example, from here you start measuring the distance of all the nodes in the tree, and for example you measure the distance between n1 and n2. Since n2 is outside of this your r radius, this is r, so this is r. So if your n2 is out, this distance between n1 and n2 is greater than r, then this means that this point will not be considered for rewiring, and we only consider the points that are inside this radius r. For example, we measure the distance between n1 and n3, and this distance is less than this radius r. It means that this point lies inside this radius, so we consider this point for rewiring. Okay, then we have here, after that what we do, we check, similarly we check the all the nodes in the tree, and we check them whether they are inside this distance r, and also they are not in collision with the obstacle. Okay. And this is something, initialization of the cost. And so here what we do, we assign the value q minimum is equal to q near. And what was the q near? Q near was the nearest point to your sample point. Okay. And then we have a cost. Since we are not using any cost, so we don't consider it here. And then we have here iterate through all nearest neighbors to find alternate lower cost paths. So now in this for loop, we shall iterate, we shall check all the nearest neighbors, and we shall check whether is there any way we can further reduce the length or the cost of the travel. So we're talking about this distance r, and within this distance we look for all the nearest neighbors of this node n1, and we check that whether we can reduce the cost or not. And keep in mind that we shall repeat this process for all the nodes. For example, once this rewiring is done, then we shall go to, for example, let's say this point here, and at this point we shall make again a radius r, and within this distance we shall see, okay, the nodes that are within this radius, can we further reduce their cost? For example, we can for sure reduce the cost between this node, let's say call it okay N4 and N5 and 6. So they are within this radius R, and we can reduce the cost by directly traveling from N4 to N6, or you can say N6 to N4, instead of going from N4 to N5 and N5 to N6. We can directly go from here to here. So this is rewiring. So after that we shall remove these connections here, and we shall say okay, N6 is a parent node of N4, and we shall remove the other edges also. Okay, so yeah, so we do this thing in this for loop. We check we check how many nodes we have within the radius R, which is Q nearest nodes, and then we check the collision with obstacles, and if there is no collision, and then what we do, we this is for cost, this is for the cost measurement. So what we do, we have a cost of the nearest node, and then we also have a distance between your new node and the nearest node. And what we do, we add both of them, and then we say that okay, if this cost is less than C minimum, okay, so C minimum comes from here, and we say that okay, if this cost is less than the sum of this, it means that we can proceed further. So what we do, we assign the value of Q nearest to Q minimum, and also this new value into C minimum, and then we plot a line here. After that, in the next step, we update parent to least cost from node. So as we did here, like here we updated the parent once we found a shortest path or a low cost path. We updated the parent of N4 to N6, and previously it was the parent of N4 was N5. Yes, so yeah, so in this for loop we update the parent node which has the least cost, or the shortest distance, and then here we add the new node in our tree. Okay, and yeah, and then there's some temporary array. Then we have, so finally here we shall repeat this step, and in this step we shall find the path by tracking the parents of each node in the tree from goal to start in a backward fashion. So let's see that how this algorithm, RRT style algorithm, works. So let's run it. And here you see that the algorithm is working, and the only RRT star, we have only these black lines, okay, the tree. And but in RRT star you can see the green lines, they are shortest distance, the new alternative low cost distance between two nodes. Let's see here, for example, this example. So from this is a tree, the black line from here to here was a tree, and you can see that if you want to go from this point to this point here, if you follow the black point, the tree, black line, sorry, you have to travel this all the way. But RRT algorithm, it has found a shortcut path, a better solution, low cost solution, and these green lines, they represent the better solution or the low cost path. So what RRT star algorithm does, it has rewired this node to directly to here. Instead of traveling this far away, it says, okay, you can directly go from here to here. And yeah, so algorithm has finished. You can see that the path is much more smoother, comparatively smoother, you can say, as compared to RRT algorithm. And it's also, it's not 100% optimal path or the shortest path, but it's near to, close to your optimal solution. And if you increase the number of samples, these points, sampling points, to high value, ideally infinite values, then you shall find this the path optimal, or the best path. Okay, so since we are only using 1000 nodes now, so you can see there are some zigzags also in this. Now let's see that how we can by further changing the values of R, what effect does we have to the output path. Just remember this figure, and now we're gonna change the value of R. So previously we have R5, and now make it 10, and again run the algorithm. You see that the tree is growing, and this time the green lines, they are larger. They're larger, and yeah, so of course this will also, I think, take more time comparatively, because now the radius is bigger. The algorithm has to search more nodes within this radius. And you have also noticed that the path, it looks better. The zigzags, they have been they are less, and the path smoothness increased greatly. There is one, for example, here there is one corner here which ideally should not be here. So if we further increase the radius R, then I hope that this path will be directly connected to here. So this will be the shortest path from here to here. But let's make the R bigger, so we get rid of this corner, that's making it unwanted. So I shall make the R bigger, and what I expect that this line will get straighter from here to here. So let's make it R15. Clearly the green lines, which represent the rewired tree or graph, they are now longer, and the tree is growing, keeps growing. The number of samples are same, they are 1000, and the EPS value. So we have found the path, but this corner is still there. So let's make the value a little bit more bigger. Let's make it 20. So this time you see that the rewiring is taking place on a larger scale. So yeah, so you see that now the algorithm has found the shortest path, likely in a very like a smooth straight line, like we see in, it can be comparable to Dijkstra's algorithm. Or so there are not much zigzags here, only zigzag is here, but I think this can further be improved if we increase number of samples, and we also decrease the EPS value, or the distance of the new point, new node. Okay, so yeah, so this was the this is the end of the RRT star algorithm and also RRT algorithm. And yeah, so now your task is to what you have to do is to, this is your task, and I expect that you shall complete it and you shall send me back by email the results you have. So this is how I give you an environment here. So this is your environment, and here you have so these are two obstacles. So this is obstacle 1. So I call it, let's say, O1, and this is O2, obstacle 2. And then you have, this is your start point, and this is the target point here, okay, goal point. And the size of your canvas is, make it 100 by 100, and the coordinates of your start point are on x-axis it is 5, and on y-axis it is 90, and the coordinates of your obstacle are this point here, the starting point. It is located at 20, on x-axis 20, and on y-axis it is 10. and then the size of this obstacle is on the x-axis. This is 10, and this one is 80. And similarly for your second obstacle, the coordinates are here. Okay, let me write down here. Okay, here we have on x-axis it is 80, and on y-axis it is 0. And the size of this obstacle is 10 on the x-axis, and on the y-axis it is 80. And now let's talk about the goal coordinates. The goal coordinates are on the x-axis it's 90, and on the y-axis it is 10. So you have to find a path that avoids the obstacle and reaches the goal using the RRT algorithm. Okay, and after that you have to find a path using RRT star algorithm. The path, the only condition is that the path should, for RRT star algorithm, the path should find the goal. It should not stop. The algorithm should not stop without finding the goal. So for that you have to find the appropriate number of samples in the environment. So you have to set how much value you have to give, and also you have to adjust the value of R and the EPS value. You have to tell that which value is better suited and gives you a better path. Okay, then we shall end this lab session. Thank you very much for joining.